Welcome to The Buzz. I'm Christopher Conover. This week, an update on a long-time space mission with major University of Arizona ties.
10 seconds. 9, 8, 7, 6, 5, 4.
What you're hearing is audio from a launch that took place on September 8th, 2016.
And liftoff of OSIRIS-REx, its 7-year mission to boldly go to the asteroid Bennu and back.
That means those 7 years are almost up.
Pump speeds and check pressure so within family.
OSIRIS-REx will land in a few months, carrying with it a sample from the asteroid Bennu. As the return nears, we're asking what humanity could learn from this groundbreaking mission. We start by checking in with Dante Loretta, the University of Arizona planetary science professor and principal investigator for OSIRIS-REx. Our conversation starts with Dr. Loretta giving us an update on the mission.
So the spacecraft departed asteroid Bennu on May 10th of 2021. So over 2 years ago, we left our asteroid with our precious cargo in hand. And quite honestly, up until that point in my life, I had thought about nothing but the asteroid encounter. What's the spacecraft going to do? How are we going to get the sample? How are we going to pick the site? And so it was this enormous sense of relief to know that we had done that part of the mission, which we had always thought was the hardest part. And so now we're switching to what I call the ground game, right? We got to do multiple things. First of all, we got to get ready to receive that capsule. It's coming down through Earth's atmosphere. It's going to parachute into a Utah test and training range, which is operated by the Department of Defense. And so there's an enormous amount of logistics that have to take place in order to make that operation proceed. And then there's the whole media production side of it. It's a history-making event. The world is interested. And of course, the sample has to get to Houston, to NASA's Johnson Space Center. So we've been doing a lot of work building the curation lab, making sure it's ultra clean, getting all the hardware in place, and reviewing the procedure for disassembling the flight hardware, which again launched into space in 2016. And then for me, the best part is this is the real science. This is a sample return mission. Our goal is to analyze that material, and we're going after the whole history of the solar system. And then really for me, did we synthesize, the royal we, were organic molecules synthesized that were critical for the origin of life? And what does that even mean? And so I've been digging a lot into origin of life investigations and trying to really understand how to frame that question with testable measurements of the return sample.
A lot of things to talk about in there, so let's back up a little bit. Let's talk about the initial return to Earth. Like touching the asteroid, which was not a sure thing. Now it is. You accomplished it. The return to Earth is not fully a sure thing.
That's correct. Yeah. So there have been 2 other similar missions in NASA spaceflight history. The first one was called Genesis, and it was a solar wind sample return mission. And the parachute did not deploy on that capsule, and it crashed into the Utah mud and seriously compromised the science from that program. The second one was Stardust, which returned dust from the coma of a comet, and that one worked. So right now, it's 50-50 in spaceflight history for these capsules coming in safely. The good news is we're the third in the line, so we've learned all those lessons. We did not make the mistakes that the Genesis mission has made. But nevertheless, this is hardware that's been exposed to the harsh space environment for 7 years. The biggest risk is the battery system inside that return capsule. That hasn't been powered on since launch. We're not going to know if those batteries are functional until about 6 hours before we release the capsule.
And if the parachute doesn't deploy, it comes in, it hits the Utah desert. Is that the end of the project?
No, we're ready for that. One of my least favorite things to do these days is to sit in conference rooms and talk about all the horrible things that might go wrong. And that's mostly what we spend our time doing these days. And we'll go out there and we'll recover whatever bits of Bennu are identifiable in that Utah desert mud. And we will do our best to characterize them and still try to recover the science.
You mentioned the landing site. You referred to it as Utah mud. How did you pick that site, and is it muddy year-round? Is it mud like me, as someone who grew up in the Southeast, thinks of?
Yeah,
Or
so
what
the
is
site where the capsule is going to touch down is part of the Utah Test and Training Range, which is a Department of Defense test range. It's southwest of Salt Lake City, and it's on those big salt flats. So the Salt Lake, the Great Salt Lake, as it evaporates, it leaves all that salt deposit behind. This is just a little bit higher in elevation than the Great Salt Lake is, and it looks like those salt flats. There could be standing water and mud out there because of these low-lying regions. If there's a lot of rain that passes through there, the capsule very well may land in a muddy region. The reason we picked that location is that is the largest continuously controlled airspace in the continental United States. So it's restricted. Nobody can fly through there commercially or privately. So it's a safe place for a capsule from outer space to enter and drop onto the surface of the Earth.
Now, you said once it touches down in Utah, you've got to get it, and I guess the smaller piece. I'm sure NASA's going to want to look at the whole thing, but the smaller piece, which has the sample in it, to Houston. How long from you recover it, everything went well, the parachutes worked, it touches down just perfectly, till you get to open it up? It's got to be like a holiday at that point, like a birthday opening a present.
Absolutely. So on the green light schedule, which is everything goes exactly according to plan, which, by the way, is how OSIRIS-REx has operated for the past decade plus, so we have a good history in that area. We should be in Houston the next day, on Monday morning, September 25th. We should get the canister into the curation lab. We'll probably rest at that point, and then the next morning, Tuesday morning, September 26th, we should drive the motors and open it up and see at least the TAG-SAM sample collector secured inside its capture ring.
Again, assuming it's all green lights, and as you said, OSIRIS-REx has a really good history of that. What happens to everything that's inside? Does it all come eventually back to the University of Arizona? But there are other partners. I'm sure they want their bits of it.
That's right. So the agreement is that 25% of the return mass goes to me and my science team. A large number of those individuals are based here at the University of Arizona, but we have almost 200 researchers, 60 different laboratories spread across 4 continents and 16 time zones. So the world is waiting for this material to land and really get going on this amazing science. The other 75% originally belongs to NASA and the international partners. So the Canadian Space Agency contributed an amazing laser altimeter instrument. In exchange for that, they get 4% of the sample. The Japanese Aerospace Exploration Agency, or JAXA, has an interagency agreement with NASA. They brought asteroid samples back in 2020, and we're giving them 0.5% of what comes back from OSIRIS-REx in exchange for that. So the rest of it is NASA's to curate for the long term.
How do you divide that up? Because I saw the video that everybody has seen now, or the stitched together still pictures. Lots of little, we'll just call them rocks from the collection, but some of different sizes. I can imagine, having talked to geologists over my career, that you might just have one sample of something of a particular makeup that's really interesting. How do you divide that up? 75% to NASA, 25% to your team?
Yeah, Chris, that's a great question. We call that the blue marble scenario. You open up the sample collector, mostly black dirt, like dominates the surface of asteroid Bennu, and then there's this shining blue marble sitting in. Everybody wants it, right? It's interesting. The agreements that are in place don't specify anything like that level of detail. It simply says we get 25% of the sample. It doesn't say which 25% or how we pick the 25%. But what we have agreed to with the agency and the curation team at Johnson Space Center is that we get 25% of each kind of material that's in that sample collector. So if there's the one blue marble, we got to split it. We got to find a way to crack it into 4 pieces, 1/4 of which belongs to me and to the science team. Now, that said, we're going to try to avoid going for the shiny object first, right? We want to understand the nature of the collection. So we're trying to be systematic, good, objective scientists and say we need to characterize the most abundant thing first. So we'll get going on that right away, and then down the road, we'll start to look at more and more rare different kinds of types of rocks that might have been brought back from Bennu. I expect there might be dozens of different kinds of material in there, and we're not going to get through it all in the 2 years that we have funding to analyze the sample.
Yeah, you just brought up something interesting about science that people may not realize necessarily. When you're funding your experiments are finished, that's not the end of it. There will be other researchers, younger researchers coming up behind you and probably behind them even. Maybe kids who are elementary, junior high now could be working on these samples at some point in the future.
Absolutely. Sample return missions are the gift that just keeps on giving. We're still analyzing lunar rocks that were brought back by the Apollo astronaut in the late 1960s and 1970s and learning new things because we're smarter, we have better instruments, we have that entire body of knowledge that's been developed since then to formulate better tests, better hypotheses, and better ideas about the early stages of the solar system. One of the great things about being a professor at the University of Arizona is that sample analysis is a great entry point for students interested in solar system exploration. These samples are going to be here. If you're a University of Arizona student and you want to work on them, come and find me because there's a lot to do. We have some of the best laboratories in the world, and we're going to be some of the first people to look at this material.
You mentioned best laboratories in the world. You all built a new laboratory with some really new equipment, cutting-edge equipment in it.
That's right. Yeah, we've remodeled the basement of the Kuiper Space Sciences building right next to the planetarium on campus here. And we have put in state-of-the-art instruments, electron microscopes. We can image the sample literally down to the atoms that make up the crystals in its structure. It's phenomenal. To see matter at that level, right? People ask me if I've ever seen an atom. I actually have, because we have an amazing transmission electron microscope that allows us to do that. And the final kind of crown jewel of the facility is hopefully arriving in July. It's called a nano secondary ion mass spectrometer. It's going to be amazing, and it allows you to look at the elements and the isotopes in very tiny regions of the sample, and those tell you the story of the history of the asteroid and its journey through space.
Let's talk about something that maybe our listeners can relate a little more to, because very few of us have ever seen an atom other than you and a handful of scientists. There's a book, I understand, coming out, pictures from the TAG event, as it's called, and it's got some famous people besides you who are involved in it, names people might know but might not know in the science world.
That's right. In fact, I just got the proof today. It's sitting in my office. The book is called Bennu 3D, Anatomy of an Asteroid. It's a joint publication between the University of Arizona Press and the London Stereoscopic Company. The London Stereoscopic Company is owned by Sir Brian May, who is also well known as a musician, being the lead guitarist and founding member of Queen. But he has a PhD in astrophysics and is an avid asteroid scientist. And he reached out to us in 2018 as we were arriving at Bennu with his skills. He does stereoscopic imaging, where he finds two images that have just the right variation in angles so that when you look at them through a stereoscope, the surface pops out in amazing three-dimensional beauty. And he produced hundreds of these stereo pairs from our encounter with asteroid Bennu. We've compiled all of those into this book. It covers not just Bennu, but it actually covers the entire history of asteroid science and meteorite science. How did we get to the point of sending a robotic probe out to visit one of these objects? And what is the science that we're trying to achieve with all of that?
That brings up a pretty obvious question, again, for people who aren't self-proclaimed space geeks like me. What is the science? Why are we doing this? Why are you and I so excited about this project?
Yeah, the OSIRIS-REx mission is really cool because it has several different high-priority science themes associated with it. What I'm interested in is the origins investigation, right? I really want to understand, are we alone in the universe? And how did life arise on this planet? What were the conditions that were required for the origin of life to occur? And it's a mind-boggling question. I call it the rabbit hole. The more you start to read about it and see what other people have done, you realize it's a profound mystery that we really don't understand. And so we're hoping for clues. I call it the recipe for the prebiotic soup, right? The idea is that the early Earth had just the right conditions, water at the right temperature, or maybe that cycled through a set of temperatures, and the right ingredients we think added from these carbon-rich asteroids like Bennu, and then something happened and life arose out of that. The other big reason is that Bennu, the asteroid that we targeted, is the most potentially hazardous asteroid in the solar system. It has the highest probability of impacting the Earth of any object that we know about. And I don't want the listeners to panic because the impact will be at least 160 years in the future, but that's not that far away. And, we as a species and as a society, we need to understand this is the most hazardous natural disaster facing us. And so we don't need to spend a lot on mitigating the risk, but we also shouldn't be spending nothing. And so our project mitigates that risk. We understand this asteroid much better. We understand the forces that drive its orbit in the future much more precisely, and we can use that knowledge to potentially deflect it if it is coming to the Earth in 2182.
I know this is a question scientists hate, but if I don't ask it, some listener out there is going to send me an email and ask why I didn't ask it. We get full green light. Everything works just perfectly on the 26th. You start dividing up the samples. You said you had 2 years of funding. So when do we find out what we know?
We should have first results out that week. We're hoping that even though we might not get into the TAGSAM, which is the collector that touched the asteroid, there should be dust all over the surfaces because of the nature of the collection. We actually saw material leaking out of TAGSAM after we contacted asteroid. It was kind of a crisis for us. Very quickly after our success, we were in emergency mode to get that stowed and prevent any further loss of sample. That means there's stuff all over the inside of the canister. So one of the very first things we do once we've got it open is we're just going to swipe it. We're going to grab a bunch of that dust and we're going to get it into the electron microscopes and other instruments at NASA in Houston. And we hope that week have some results to report to the public about at least what the first look mineralogy and chemistry of the sample is. Most importantly, is it what we're expecting or is it something completely different?
Which sends you in some ways back to the drawing board, and that's
right.
The fun of science.
If it's not what we're expecting, the spectroscopists, those are the scientists that analyze the light that's reflected off the surface and the heat that's emitted, they were pretty sure they identified a series of minerals on this asteroid. If they're not there, they've definitely got to go back and revisit some fundamental assumptions about their science.
All right. Well, I know you're going to be very busy between now and 2 years from now, but we'll talk again.
Sounds great. Thanks for having me.
That was Dr. Dante Loretta, the lead investigator on the OSIRIS-REx space mission and Regents Professor of Planetary Science and Cosmochemistry Lunar and Planetary Laboratory at the University of Arizona. You're listening to The Buzz. I'm Christopher Conover. We're taking a look at the OSIRIS-REx space mission this week, which is due to land in just over 3 months, bringing with it samples from the asteroid Bennu. To learn more about what this mission could mean for those who are not immediately involved, I spoke with Dr. Erica Hamden, a professor of astrophysics at the University of Arizona and host of the AZPM TV production New Frontiers. I started by asking her why the OSIRIS-REx mission should appeal to the broader society.
I mean, first, because it's cool and people should care because it fulfills a very basic human need to understand more about the world around us. And that's just a really basic part of being a person, is that you want to know more and understand more and wonder about why things are the way that they are. I think more practically, the sample return is a really exciting opportunity to get our hands on stuff from space, which is extraordinarily rare. We brought back moon rocks from Apollo. Sometimes meteorites land on the Earth that are from Mars. And that's it. Sample returns. I mean, there's been a few other smaller missions that have gotten samples from stuff in space and brought things back, but I think there's a total of less than 5 instances of things coming back. Each of those bodies, the stuff from the moon, stuff from Mars, stuff from Bennu, it's all different. The composition is different. It's had a different history, and it tells us really important information about how the solar system formed. And when we especially connect that to planets that we're observing around other stars, and we don't really know how they form exactly, and what conditions are needed to form something like the Earth, and what happened in the early solar system that made it possible for the Earth to form and for the Earth to be just the right type of planet to make life. So even though you're like, oh, we're just bringing a bunch of rocks back from somewhere, like A, that doesn't happen that often. And B, the rocks are important for us to understand, like, how did we get here?
I am a self-admitted space geek, but it seems to me we're in another maybe golden age or starting of another golden age of space exploration. We had all that stuff going on in the 60s with Apollo and going to the moon. And then we had Voyager and some of the stuff in the 70s. And things seem to have quieted down, but all of a sudden now we have the James Webb Telescope going. We have big earthbound telescopes, many of which are built at the University of Arizona in part. We have projects like OSIRIS-REx, all the cool stuff going on Mars right now, a project that you're co-PI on that we'll talk about in a minute. Is it just me, or are we in a new age of exploration?
Well, I think we are in a new age of exploration. It's gotten a lot cheaper and easier to send things into space, not just people, but like satellites or telescopes. But it's also like all the components of satellites, all the like hardware that you need for like telemetry and communications and power, like all of that is cheaper. Before, if you wanted a spacecraft, you'd have to call like an aerospace company, and then you'd have to get a ride on a rocket that is super expensive. And now there's rockets going up all the time. You can like find these commercial vendors where you can buy parts of a spacecraft like on the internet as if you're ordering something from Amazon. Those components of getting into space are a lot less expensive. And I think there's also like space is very in, or it's very popular. It's interesting. I feel like there was a bunch of movies about people going to space. Not all of them were, the outcomes were not positive. It doesn't make you want to go to space. But like space has just, I think, entered the public consciousness in a much more obvious way. And I also think with like the rise of social media, it's easier for organizations like NASA to get the kind of the word out about what they're doing to a broader audience. I think it's really good because more people being into space and being interested can help to increase funding for all the different aspects of space exploration. It can also be tricky because what you don't want is for it to be like a trend or a fad that then goes away. But I think if people feel like they have like more of a personal connection, or that like there's a chance that they could go to space, like some of these companies are doing like contests, or they're looking for like citizen astronauts and stuff. And I think that helps people to feel like, oh yeah, this matters. This is important.
Well, and you mentioned social media and NASA, and when people think of space, they of course think of NASA, but then there are people like you doing space research. You have a huge social media following, and you've made it cool or interesting at the very least.
Yeah, well, it's fun and easy for me. It's interesting because the stuff that I feel like, oh, every person knows, this is going to sound insane, but like every person knows what powers a star. Like I've known about that since I was in like third grade, but that's not true. Nobody knows what powers a star. So stuff like that where I'm like, oh yeah, like let's talk about fusing hydrogen to helium. But there's actually like surprisingly there's a real interest, like people want to know, and there's a huge swath of people who for whatever reason like don't know how to find that out. But then if someone is explaining it to them in a way that's accessible, they're like, oh my God, I love this.
Well, and talking about accessible, I have to ask one thing about you, because I was looking at your CV before we did this, and you and I, because of your work here around AZPM, have also chatted in the halls a couple of times, but I just discovered you're a chef, like trained Cordon Bleu Academy chef. How did you go from that to PhD astrophysicist?
They're actually more similar occupations than you would guess. When I was growing up, I would tell my friends like, oh, I either want to be an astronaut or I want to be a chef. Those were my two like career tracks. So after college and before grad school, I went to Le Cordon Bleu, and then I worked in a restaurant for a little while. It's a really tough job. It's a hard job. It's like extremely underpaid, and there's long hours. You get burnt all the time. I had applied for grad school when I finished college, and then I deferred my acceptance. So after I was working in the restaurant for a little while and I was feeling like, oh, this isn't as interesting as I want it to be. I was feeling like bored. I felt like, okay, well, I've tried this and now I want to try something else. But what's interesting is like the issues I had with being a chef, the hours are really long, especially the first like decade of your career. You're like laboring for somebody else's creative vision. And if you're lucky, one day you'll get trusted enough to have your own place that like it's your creative vision that everyone else is carrying out. And you don't get paid very much, you work a lot. Then I went to grad school and it's like almost exactly the same thing.
To say that sounds very similar.
You get paid not very much and you work a lot and you're carrying out somebody else's creative vision. It's just applied towards like a scientific question and not, what's the menu going to be. But it was fun and like an interesting experience for me to try it. Maybe if I had stuck with it like 10 years later, I would have felt like, oh, this is intellectually engaging. But at the time, I was just like, I miss thinking about galaxies and the universe. And so then I was like, okay, this means that I should go to grad school. So then that's what I did.
So let's talk about the interesting stuff that you're working on. As we alluded to, you are the co-PI on a project that's launching in 2025, which sounds like a really long time away, but we'll be here sometime in the next week. All of a sudden, we're going to turn around, and there it'll be.
I'm the deputy PI. Our PI is Carlos Vargas, who's another professor at the university. In the world of telescope building, like 18 months is like zero time. So we're like in the final stages of the designs. We're starting to order parts, and we're getting like the mirrors, for example, for the telescope are getting coated. The mirror is made of glass, and then you put an aluminum coating on it to make it reflective. So that's happening like this month. Then we'll put everything together in the early part of next year. And then we ship it to our spacecraft provider, and they integrate the instrument into the spacecraft, and then they'll ship it to wherever it's going to get launched from.
What are you all hoping to see? I mean, I know it's a vast universe out there once you get out there.
So our objective is to look at very nearby galaxies to the Milky Way. And we're looking at galaxies that are what we call edge on. So if you imagine like a beautiful spiral galaxy, you see the spirals if you're looking kind of at the face of the galaxy, but you can tilt it and then you just see like a line. So you're like looking along the plane of the galaxy. And we are targeting that type of galaxy because we're actually not really looking at the galaxy itself. We're looking at the stuff that's above and below the galaxy. And the idea is that these galaxies are forming stars at a certain rate. And in order to do that, they have to have access to new hydrogen that's coming in from farther out into space. We're not actually directly looking for the hydrogen. We're looking for oxygen emission. But those oxygen atoms will be like associated with these big clouds of hydrogen. And we're just trying to understand like what's the environment of the galaxy look like. There's a bunch of simulations that, each simulation has slightly different predictions of how these environments should appear, but we don't actually have maps of them because the mission that we're looking for is really faint and it's at kind of a challenging wavelength. So we're trying to kind of map and understand the dynamics of this like pretty complicated environment. So it's a challenging observation, but it's something that people have been talking about doing for like 60 years, and we're finally going to do it.
Well, good luck. And for any of our listeners who might have gotten a little bit lost, I'll point you towards Dr. Hamden's Instagram page. It's probably explained there in more bite-sized chunks. and your new show you're doing with us, New Frontiers, on our TV side. So thanks for spending some time for us. I know you're in the lab at Caltech right now, so we'll let you get back to work.
Thanks. It's really great to talk with you.
That was astrophysics professor Dr. Erica Hamden. And that's the buzz for this week. If you want to watch a live taping of our show, we've got that opportunity coming up. In July, we're heading to Douglas, Arizona to talk water and the newly approved by voters active management area. We'll have details on our website soon. You can find all our episodes online at azpm.org and subscribe to our show wherever you get your podcast. Just search for The Buzz Arizona. Zach Ziegler is our producer with production help from Desiree Tucker. Our music is by Enter the Haggis. I'm Christopher Conover. Thanks for listening.
Arizona Public Media's original programming is made possible in part by the Community Service Grant from the Corporation for Public Broadcasting.